Hey, howdy everybody. So now that we've covered Kriging for spatial estimation, and we covered the sequential Gaussian framework for simulation of continuous variables, now we should cover the idea of indicator-based methods for the purpose of estimation and simulation. So what can we say about indicator-based methods? We can use them for the purpose of estimation and simulation when we're working with categorical variables. And specifically, we benefit from the fact that we're able to explicitly control the spatial continuity of each category. In fact, the most common use of this type of methodology, indicator-based methods, are in the cases where we have categories or discrete variables. We can also use them for the purpose of estimation and simulation with continuous variables and benefit from the added explicit control of spatial continuity for different magnitudes. In the last section, we talked about the fact that the sequential Gaussian paradigm results in a maximum entropy type features. These are recognized as very short, or maximum discontinuity, I should say, for the extreme values, and greater continuity for the values in the middle of the distribution. This, of course, can be problematic if we consider the most important values with regard to our distributions of porosity and permeability are in fact the values at the very ends of the distribution. Those are the very low permeabilities and porosities that may form our barriers and baffles, and those at the very high may be our conduits to flow, have the most important impact on flow and behavior. In order to work with indicator-based approaches, we need to indicator code our data. It's interesting, this indicator coding is effectively a probability coding based on categories or thresholds. Categories if we're dealing with categorical data, or thresholds if we're dealing with continuous data. And it requires us to infer indicator variograms for every one of the categories or thresholds that we're working with. A little bit more work, but the concepts are quite straightforward once we understand variograms and typical type of simple Kriging and so forth. So what are we doing when we are using indicator methods? So let's talk about the indicator coding. We're transforming a random variable or function, or the data, to a probability relative to a category or a threshold. What does that look like? Well, we denote it like this. The indicator transform at location u bold as a vector, a location vector, for the threshold or category zk is the indicator threshold for a categorical variable. And what is it? It's what is the probability of a realization or data value being equal to a specific category. So the indicator transform at location u for category zk is going to be 1 if at location zu the random variable or the data is equal to that category. And it's equal to 0 otherwise. So I'll give you an example. We have threshold 2, which is equal to 2. That's categorical, so it's in fact a category. And we have a data value at location 1, u1, which is equal to 2. The indicator transform will then be equal to 1. 100% chance at location 1 that we have category 1 because the data value at that location is equal to that category number 2. And we could have another example here where we have a threshold of 1, but then we have a random variable. We have some type of soft constraint for data, not hard data. And so the indicator transform would indicate that we have a 25% chance of that category occurring. It's not 1 or 0 because it's soft constraint. The indicator transform, if we have a continuous variable, is now we're going to be talking about what the probability is for realization to be less than or equal to a threshold. And so our indicator is defined like this, where it's 1 if the random variable or the data is less than or equal to that threshold, and 0 otherwise. So examples would be, given a threshold, number 1 of 6%, it could be porosity. The data value at location u1 is in fact 8%. What's the probability of it being less than or equal to 6%? 0. So the indicator coding is 0. And of course we could have a location, well, so we have location 2, we have a threshold 18, and at that location we have soft information described by a Gaussian distribution, and we can calculate the probability of being less than or equal to this threshold of 18%, and that turns out to be 75%. That would be the indicator or probability coding of the data. Now, just in case this concept of indicator coding is not clear to you, I have provided a table where we have a set of data, location 1, 2, and n. So there's n data. And we have 3 different possible categories, 1, 2, and 3. And we have the indicator transform relative to category 1, category 2, category 3 at all locations. And so the indicator transform for the first location, which has a true value of 3, it's hard data. The probability the category is equal to 1, 0%. 2, 0%. 3, 100%. Location 2, the actual category at the hard data is equal to 1. So the transform is for category 1, 100%, for category 2, 0%, 0. And you see hard data will result in this. These categorical hard data will just be simply 1 or 0 if we have the actual value in that location. And so this is a probability coding. We take our original data vector, which has 1 column by the number of data, and of course they'd all have locations and so forth. And we convert it into an array with k columns, where k is the number of categories. And so that's what Indicators does. It actually converts our data into k separate sets of information or probability codings. And of course we could look at the case where we have a variable. And so now we have data values at 1, 2, and n as 12%, 4%, and 17%. And our thresholds are 5%, 10%, and 15%. These could all be porosities again. What's the probability that 12% is less than 5%? 0. 0 for 10. And 1, it's less than 15%. Probability of 4% being less than these thresholds? 100%, 100%, 100%. 17% is larger than all of the thresholds, 0% for each of them. And so you can code your continuous data relative to each one of the thresholds like this. Then we can use these indicator transforms or indicator-based probabilities for spatial estimation for each one of the categories or thresholds. And so what we're doing with indicator Kriging is we're going to discretize the interval of the variability of the continuous attribute z into a series of thresholds. If it's categorical, of course it's a bit different, but we'll discretize it into thresholds. Then we'll perform indicator Kriging to estimate at those thresholds at the unknown locations using the indicator transforms for that threshold of all of the neighboring data. And the indicator-based variogram will get into that. And then we'll say that that is going to be equal to the probability at that unknown location, the estimate at that unknown location of the true value being less than or equal to that threshold given n, where n is your available data within the neighborhood. And so this is very powerful. We actually are estimating a conditional CDF or conditional distribution directly at the unknown location with no distribution assumption, but as a series of thresholds. For a categorical case, it's very straightforward. In that case, we're going to be estimating the probability of being equal to a specific category. And if you imagine, if we estimate the probability of being in each of the categories for all possible categories 1 through k, that in fact would provide you with an entire distribution of uncertainty for the categorical or discrete case. And just to reiterate, we use the term conditional CDF, or we can call it a CCDF, is a CDF at an unsampled location estimated by local data. It's conditional to the data. As opposed to a regular CDF, we calculate from the data. Now we're talking about a local estimate of a CDF conditional to neighboring data. All right. Indicator Kriging. What does it look like? Well, this is how we could express it. In fact, we are going to estimate through indicator Kriging the probability at an unsampled location for a specific category, or the cumulative probability at a threshold, and we'll do it based on a linear set of weights applied to the indicator transforms of all the available data, and we will also account for the global proportion if it's categorical, or the global cumulative probability if it's continuous, the initial input distribution. And so 1 minus the sum of the weights will go to that. And so if we have no information, we just estimate with the global distribution, continuous or categorical. And this is pretty powerful. What does it look like in practice? Well, you have an unknown location, you have data 1, 2, and 3. The data will be broken up, and the distribution at the unknown location are broken up into a set of thresholds, 1 through 4. And we have the data will be coded based on those thresholds. So you could imagine that there, based on the magnitude of the data values, we'll have a transition over the thresholds from 0 to 1, 0 to 1, based on the actual data magnitudes. And so then at every one of those thresholds, we'll perform indicator Kriging, and we will estimate a cumulative probability at that threshold. And we repeat it at the next threshold, the next threshold, next threshold, and in the end, we get a local conditional distribution at that unknown location. And so this is very cool. We're estimating directly the distribution of uncertainty. Compare and contrast that to the Gaussian type approach or the simple Kriging type of approach, where we were estimating the mean and the estimation variance or the Kriging variance, and then using a distribution assumption to then get a local distribution of uncertainty. In this method, we actually build the CDF up by discretizing the problem at different thresholds, estimating their cumulative probabilities, and then we'll use a piecewise linear model or some other type of interpolation method. We'll have to do some tail extrapolation, and there we go. Et voila, we have an entire distribution available to us that we can then use for any purpose, and we'll make a comment on what we're going to do with that next. Of course, if it's categorical, this works perfectly well with categorical cases. Our classes are going to be K1, K2, K3, different categories. We're going to estimate independently their probabilities at the unknown location, the unsampled location, and we're good to go. We now have a distribution of uncertainty for categorical and a distribution of uncertainty for the continuous case at the unsampled locations. Well, so what do we have to do to make this happen? We have to use the indicator transform on all of the data. We have to calculate an indicator variogram, and then we have to use indicator Kriging with the transform data and that variogram to estimate the probabilities at the unknown locations. And so let's go through each one of those pieces. Let's talk first of all, we've already talked about the indicator transform. Let's just kind of finish a couple points really quick about the indicator variogram and what that looks like. So what do we have? How do we calculate the spatial continuity for the indicator approach? This is the indicator variogram right here. It looks just like the regular variogram. In fact, the only thing that's different is that now we are using the indicator transform of the data, and we're doing that for each one of the thresholds or categories. So you'll notice that our indicator variogram is not just gamma. We put an I, gamma indicator, at H. It's not just H, it's also going to be a function of the threshold. It'll change with each one of the thresholds. Another thing that's very interesting about this, the indicator for hard data is either 0 or 1. So what do we expect? If we look at the summation, we're taking an average, 1/2 the average of a summation of this square difference. Well, if both of them are equal to 0 or both of them are equal to 1, i.e. they both belong to the same category, or they both aren't in the same category, or they're both either above a threshold or both below the threshold for the head and the tail in space, those cases will always render a 0, because we'll have the 1 minus 1 or 0 minus 1, that's 0, and you square the 0, you get 0, and so that doesn't contribute to the sum. There's no contribution to the sum. If they're different, one's inside the current category and one's outside the current category, or one's below the current threshold and the other one's above the current threshold, in that case we get 0 minus 1, which would be equal to -1, square it, it becomes 1. Or we get 1 minus 0, square that, it becomes 1. So what is it? An indicator variogram is going to be equal to 1/2 the proportion of pairs that change. So we can look at an indicator variogram and interpret it as the probability of change over distance. And that's very powerful. Another point we should make, and we've hinted at this before, you're going to need a different variogram model, or you should build the variogram model. In other words, calculate the variogram, fit the variogram, interpret and fit the variogram model that's positive definite to each one of your thresholds or to each one of your categories. And so you'll have to do that. Now you're going to standardize them so that they each have a CIL of 1. In order to do that, you have to account for the fact that the variance of the indicator is actually going to be equal to P times 1 minus P, which is the proportion of 1s and so forth. But you go ahead and you standardize them so that they all have a CIL of 1 in order to work with them. And then you're going to model multiple variograms that are positive definite. Now, just a warning. For the first cutoff, you can't say 100% nugget effect. Second cutoff, super high continuity. Third cutoff, nugget effect again. If you modeled willy-nilly so that they are changing dramatically between thresholds, of course that's a contradiction. You'd expect some consistency between the indicator variograms. They can't just change dramatically. And so what do? You want to use data to support the modeling and make sure that you're using data consistently. And you also want to, when you do build the model, think about making the changes smoothly varying between them. If you don't, you'll probably run into issues with order relations, and we'll talk about that more later. And also, in addition to that, by working in that manner, it's a little bit easier to infer the parameters in the case of sparse data. Back from helping a student who just showed up, and so how can it help us with sparse data? Well, we have information from each one of the thresholds or cutoffs can help each other. And note here we say cutoffs. This is how we posed it in the book, but we're referring to thresholds as we've been talking about. Right now, this would be 1 through K thresholds as described up till now. So some general comments about the indicator approach for estimation and simulation. You're going to need a variogram for each threshold or category. So it's a bit of a more difficult inference problem, but we'd argue that it provides greater flexibility because you can constrain the spatial continuity for each one of the thresholds or categories. The resulting model of uncertainty is not Gaussian. In fact, you can avoid that whole maximum entropy issue and create models with greater continuity for the extremes than you could with the Gaussian assumption with, say, sequential Gaussian simulation, as we discussed last lecture. More readily, you can integrate data with different degrees of softness into your conditioning, and we will talk more about how we incorporate soft data pretty quickly. You may also you can also use this approach for sequential indicator simulation, and we'll demonstrate that as an extension on the indicator Kriging right away. The methodology for sequential indicator simulation is commonly used for categorical variables like facies, and it's sometimes used for continuous variables like Pyrcz. So let's go ahead and go through the indicator Kriging workflow. We're going to loop, of course, across all locations for which you do not have data available. We're going to also, this is an additional loop, in addition to what we saw with the simple Kriging workflow, we're going to loop over all thresholds or categories. For each threshold, we're going to find all the relevant data N. We're going to code that data to an indicator based on the current threshold or category. Then we're going to use that indicator coding. At the current threshold, we'll be able to make an estimate of the probability, either the probability of being within a category or the probability, cumulative probability at a specified threshold. We're going to correct that distribution for order relations. We'll get a little bit more into order relations later. And then we're going to use that distribution. Now, so this is very interesting. At all locations when we do indicator Kriging, we're not going to have a single best estimate like we had with simple Kriging. Instead, we're going to have cumulative probabilities at thresholds. So we're basically estimating a complete CDF, or it's going to be the probabilities of being within each category. So we're estimating directly a categorical PDF. Either way, we are getting at a continuous or categorical conditional CDF at the unknown locations. So if somebody asks you to do indicator Kriging and build a single map, you could ask, well, what do you want to see? Because I in fact have multiple probabilities describing an entire CDF. So what can you do with that? You could get a measure of the uncertainty, probability intervals, percentile ranges, or something like that. That could be useful. You could assess the probability exceeding certain given thresholds. That could be useful. For instance, what's the probability that you have a contaminant concentration that's greater than some legal limit? That could be very useful to you. You can try to do expectation type estimates where you look at all of the thresholds and you look at the distribution shape and you integrate and assess what is the expected value from the distribution. You can do that too, or you could do stochastic simulation. Let me go ahead and illustrate what indicator Kriging looks like. We'll do it by hand on PowerPoint. So we have an initial distribution. Cumulative distribution function is shown right here. And so this distribution is for, say, porosity, and that's over all of the possible data we have available to us. Now we're trying to make an estimate at this unknown location, given the data at 1, 2, 3, 4 locations, and we have assigned 4 thresholds to our CDF to describe it. Now what are we going to do? Well, we assigned our thresholds. We need to calculate indicator variograms for each one of these thresholds. So you do the indicator transform, and so I've just provided an example right here. And so we have 12, 19, 14%, and 15%. What's the probability of being equal to or less than those thresholds? And this one should be 1. Thank you for the correction in class. I think that was Alex. Appreciate that. And so we would assign 0, 1, 0, 1. And you can look back and you can say, yeah, 15% is greater than. That would be 0. 14% equal to. 19% greater to. And 12% is less than. And so we would have indicator codings like that. We can then calculate the indicator variogram of that data set over all of our available data, even away from this location. We're estimating all of the data that's available to us. We would calculate the indicator variogram. Next, we would perform indicator-based Kriging, which simply would be taking our indicator variograms to populate a covariance matrix. We would have a set of these matrices for each threshold. We're performing an independent Kriging for each threshold. The first threshold, we calculate all of the covariances between the data and themselves, the data and the unknown location, and when we do that, we get a Kriging estimate of the probability, cumulative probability of 14% of being 15%. That means we have a 15% probability at the unknown location of having a porosity less than or equal to 14%. Cool. So we can repeat that again. We do the indicator coding at the 16% threshold. You'll notice that we had a change now, that this data location, because it was 15%, is now less than 16%, where it was greater than 14%. And so now we have 1, 1, 1. You'll notice that over the thresholds, as we go through them, more of the data get coded as ones. So it makes sense that there is some monotonic, not perfectly monotonic perhaps, but there's a tendency towards increasing as we make these estimates. That makes sense. So we get another estimate, 60% chance of being 16% porosity or less. And we finish up with all 4 categories, or thresholds I should say. And now we have 4 points describing our CDF. Now that's not enough to do Monte Carlo simulation. We could use some type of piecewise linear interpolation or some other type of interpolation, and we have to do some work to estimate the tails. Tail extrapolation decision needs to be made. Once we've done that, we have a complete CDF, and we're good. We got a CDF, we know the uncertainty at this location. Well, once you have that CDF, you could do Monte Carlo simulation from it and get a simulated continuous porosity value. If you take that value, put it in with the data, treat it as data, and for all subsequent calculations, you do the indicator transforms on that too, that would be very powerful. Now you have a simulation method. Now I should mention you would pre-calculate the variograms, indicator variograms, over all of the available data with the indicator transforms. You get 1 variogram for every indicator transform, or every threshold I should say, or category. And you would systematically use that. The new simulated values would not be used for variogram calculation. They would only be used for conditioning the additional indicator Kriging calculations. So you'd have to calculate all of the indicator transforms on each one of those to proceed. So one of the great strengths of the indicator-based approach is the ability to directly integrate soft data, not just hard data. Now, hard data is not a big deal. In fact, we've been showing you examples up until now of a lot of different hard data. This is exactly how hard data would be encoded with the indicator-based approach. The probability of being less than or equal to a threshold would be 0 until the point at which the data is less than the threshold, and then it would jump up. And so the data value would just jump up as soon as we got to the actual value of, say, 15% porosity here. But the cool thing about the indicator transform is that you don't have to provide a 0 or 1. You can in fact say, well, listen, the porosity is between about 17% and about 33%, and in between there's a probability based on this curve right here. That would be soft data. You're encoding it as saying that, well, yeah, it's more likely in the middle, but there's some probability to be on the tails. You could even do an inequality constraint, and that's really cool. What that means is that for thresholds that are between 20 and 30, you just don't say anything. You don't have any information about how it's behaving. But you do know that the data is showing you that the value must be greater than 20, must be less than 30. And so this constraint is saying the data tells us it's between here and here, but doesn't tell us anything else. And so we can actually encode that in an indicator transform as this inequality constraint. All right. Now let's just mention order relations. What does order relations correction do? And so this is a problem that we have, is that if we're calculating an indicator-based approach to get a CDF, we in fact are going to be calculating at each individual threshold the value. So look, we could have a value here, 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 here, here. Now if I was to go ahead and draw that CDF, I hope I can convince you that that is not an appropriate CDF, because a CDF to be valid must be monotonically increasing or have zero slope. If it's decreasing with negative slope, it suggests negative probabilities, which are not possible. And so what do? Instead of using those original points, what we simply do is we impose a non-negative slope, and we go through and we connect the points. We go to this point here, and we go up here, and then we say, well, the next data is down here, but we can't go there, so we'll just go across. Next data is still low, we'll go across. Okay, we're fine now. Okay, now we'll go to the next data point, next data point. Okay, oh, this one's down low again, so we'll just go across to it, and then we'll go up to 1. And then we're good. Now, you'll notice that would create a bias. We would be higher systematically, and so we've got another possible solution. So what we do is we go backwards. And we go down to that first point, we said, well, we can't go up or negative slope going the other way, so we'll just go across, go across. Okay, now we're good again. We can go down to the next point, go down to the next point. Oops, we can't go up, so we'll just go across. And then what we do is we just take the average of those two lines, and that becomes our solution. And that avoids any bias and imposes the constraint of non-negative slopes. And so that's order corrections. Now, categorical variables, of course, we're going to be estimating the probabilities at unsampled locations of each one of the categories. It could be boundstone, wacky stone, mudstone, and so forth. And so we will be considering a set of categories. The point we should make is that the order relations correction for this is pretty straightforward. If these don't sum to 1, all we have to do is just divide by the sum of the probabilities, each one of them divided by the sum, and that would standardize them all to then sum to 1. And so that's the approach for correcting order relations in the case of a categorical variable. Now, let's look at some example indicator simulations now. We got a categorical indicator simulation right here, taken from a paper by Michael, 2009. And it's sand, silt, or clay. Yellow, kind of a gray, and a black color. And so if you look at them, you can see the general type of behaviors. If you look carefully, you might notice or convince yourself that definitely yellow has different spatial continuity, definitely a different proportion than of the others. It's more continuous though. And you'll see that they can each have their own continuity, their own proportions. They could even have trends and so forth. And so this is the type of simulation that could be used to then constrain porosity permeability within each of the facies. Then we have this example right here. It's a continuous simulation in which we have a V-shale model. We have multiple models. This realization 1, 2, and 3, and it's taken from the book Mihan and Verma, 1994. And so you can see the basic kind of spatial continuity. Notice it's not Gaussian. We don't see maximum disconnectivity of the highs and the lows, but in fact, they each have their own spatial continuities. I should mention that there is kind of a degree of discontinuity between the thresholds. You can actually probably estimate where those thresholds are based on where things get a little bit broken up, somewhere around yellow to green, somewhere around green to blue. There's some things getting kind of broken up a bit. That's a known artifact with continuous indicator-based simulation, that you don't reproduce quite the right connectivity between the thresholds, get a little bit too broken up. And so of course that could be a concern, and that's a reason why many don't like to use this approach, but at the same time it is a possible approach to work with. Now, what else do we have available to us? Well, what I did was I went in Excel and I created an example of indicator-based simulation. I just put it together as a nice little template for the students to get a little bit of experience working with it. So let's go ahead and look at this sheet right here. This is the one where I have indicator-based, I should say indicator-based Kriging. And so as usual with my Excel spreadsheets, you can change the yellow, but you can't, the orange are the calculations, and there's intermediate calculations and so forth for the Kriging systems. But let's go ahead and just look at it and understand what's going on here. So what do we have? We have the input where we say we have category 1, 2, and 3. So you get to decide what are the categories. 1, 2, and 3 are quite straightforward. Then you have the proportion of each. We set the last proportion to be 1 minus the sum of the other two, so that we sum to 1 as we should. And then that's plotted down here. So that's the global proportion of each one of the categories. Then we have data. The data 1, 2, and 3, and their locations 1, 2, and 3. And then we have the unknown location right here. Now I'm not sure if that's 1, 2, and 3. I just picked and said 1, 2, and 3. Let's see. 50 by 40. So this is 1. 20 by 90. This is 2, and this is 3 right here. And the unknown location is right here. The data values at those unknown locations are set to be toggled by what are the categories available previously, and these are the indicator transforms for each one of them. It's quite trivial. And then you can specify the Variogram models for each one of the thresholds or categories. They each have their own Variogram models. Nugget effect will be the CIL, or 1 minus the contribution of the spherical, so no nugget effect here, 300 range. And then what will happen is you will then have the Kriging system. Notice there's 3 separate Kriging systems, one for each one of the indicator transforms for category 1, 2, and 3, using the specific variograms for each one of those categories. And the result is that you get a set of weights that will be applied to the indicator transforms of each one of the categories in order to get the estimate. And so if we look across and see where we got the Kriging estimate that's being made for each one of the proportions, you can look at it very quickly. You can look at it very quickly. You can observe that in fact that estimate is simply going to be the indicator transform of each one of the data applied, right here, multiplied by the weight to each one of the data. And then we'll take this 1 minus the sum of the weights and we'll apply that to the global proportion. And by doing that, we get our Kriging estimate of the proportion of 1 at the unsampled location. And we get the Kriging estimate of proportion of 2, or probability of 2 at that location, and the Kriging estimate of the probability of 3 at the unsampled location. And that's the resulting distribution right there. Now I suggested a couple of ideas. Let's just try 1 or 2 of them out right now. First thing we could do is let's set the range as very small. Okay, we set the range as very small. What happens? At that point, we're now estimating with the global distribution. There's no information from the data whatsoever. Now on your own, go ahead, take the sheet and go ahead and try some of these other ideas out. Place at one of the datum at the unknown location. See if we have an exact estimator. Does it estimate with the category at that data location? Set all the data to the same category. See what happens then. So there's a couple other things you can try out. Let's make a summary here. So summary of indicators. So first of all, you need indicator transform. It's a probability coding. You can work with thresholds of a continuous variable, or you can work with specific by category assignments if it's categorical variables. You can work with it for spatial estimation, and in that case you're estimating directly the CDF you're estimating the CDF by estimating the cumulative probabilities at thresholds or estimating the probability of being within each of the categories for a discrete case. Indicator for spatial simulation. What you can do here is you replace simple ordinary Kriging with indicator Kriging in the sequential context. You do Monte Carlo simulation from the CDF that you got from the indicator approach. You transform the value with the indicator transform based on each threshold, and you use it for data for the subsequent indicator Krigings. All right, so that's all we have to say about the indicator methods. As always, I hope that this was helpful to you. I'm always happy to discuss. I'm easy to find. I'm Michael Pyrcz. I'm a professor here at the University of Texas at Austin. I'm also on GitHub and on Twitter. I'm the Geostats guy, and I'm always happy to discuss. All right, thank you.